Welcome to this presentation on C++ thread synchronization. Today we're diving into the world of coordinating threads using mutexes and locks to ensure data integrity and prevent common concurrency issues. Thread synchronization is important in multi-threaded programming. The problem is that when multiple threads access shared resources simultaneously, race conditions can occur, leading to several common issues, including data corruption, unpredictable program behavior, and hard-to-reproduce bugs. The solution involves thread synchronization mechanisms, which ensure controlled access to shared resources. In C++, there are several synchronization tools available, including mutexes, which stand for mutual exclusion, locks, which are resource acquisition as initialization wrappers, atomic operations, and condition variables. Let's consider an example of a race condition. Here's a problematic code snippet without synchronization. This code includes IOStream, thread, and vector libraries. The integer variable counter is initialized to 0, representing a shared resource. The increment function increments the counter variable 1,000 times in a loop. The problem is that this code has a race condition because multiple threads can access and modify the counter variable simultaneously. The increment operation counter is not atomic, meaning it involves reading the value, incrementing it, and writing it back, which can lead to conflicts when multiple threads are involved. Now let's introduce mutexes, which stands for mutual exclusion. Mutexes are used to protect shared data in multi-threaded environments. Here's an example that includes the mutex library. An integer variable counter is initialized to 0, and a standard mutex variable Mutx is declared to protect the counter. The safe increment function locks the mutex before accessing the counter, increments the counter, and then unlocks the mutex. A mutex ensures that only one thread can access the protected resource at a time. The lock method blocks until the mutex is available, and the unlock method releases it for other threads. Let's explore a safer way to use mutexes with resource acquisition as initialization, or RAII locks. Here's an example using standard lock guard. An integer variable counter is initialized to 0, and a standard mutex variable Mutx is declared. The safe increment function uses standard lock guard with the mutex to protect the counter. Standard lock guard is an RAII wrapper that automatically locks the mutex when constructed and unlocks it when destroyed. This prevents forgetting to unlock the mutex and handles exceptions properly. When the function exits, either normally or due to an exception, the lock guard's destructor automatically releases the mutex. Now let's explore standard unique lock, which offers more flexible locking compared to standard lock guard. Here's an example. A standard mutex variable Mutx is declared. The process data function uses standard unique lock with the mutex. Unique lock can be unlocked and locked manually, works with condition variables, and supports deferred locking and lock transfers, providing more control over the locking mechanism. Let's discuss deadlocks, which are a common threading hazard. Here's an example. Two standard mutex variables, Mutex1 and Mutex2, are declared. Thread A locks Mutex1 and then tries to lock Mutex2. Thread B locks Mutex2 and then tries to lock Mutex1. Deadlock occurs when two or more threads are waiting for each other to release resources, resulting in all threads being blocked indefinitely. This can happen when threads acquire mutexes in different orders, leading to a circular dependency. Now let's explore how to avoid deadlocks using standard lock. Here's an example demonstrating how to lock multiple mutexes safely. Two standard mutex variables, Mutex1 and Mutex2, are declared. The safe operation function uses standard unique lock with deferred lock for both mutexes. Standard lock is used to lock both mutexes without causing a deadlock. Standard deferred lock creates the lock object without immediately locking the mutex. This approach ensures either all mutexes are locked or none are, preventing deadlocks. Starting from C++ 17, Standard scoped lock provides a simplified way to lock multiple mutexes. Here's an example. 3 standard mutex variables Mutex 1, Mutex 2, and Mutex 3 are declared. The process data function uses standard scoped lock to lock all mutexes at once, avoiding deadlocks. Standard scoped lock combines the simplicity of LockGuard with the deadlock avoidance of standard lock. It is a variadic template that can lock any number of mutexes at once, automatically using the deadlock avoiding algorithm. Let's go over some best practices for thread synchronization to ensure safe concurrent programming. Use RAII lock wrappers preferring standard LockGuard, standard unique lock, or standard scoped lock over manual lock or unlock calls. Minimize lock duration by locking mutexes for the shortest time possible to reduce contention and improve concurrency. Maintain consistent lock ordering by always acquiring multiple mutexes in the same order to prevent deadlocks. Consider lock-free alternatives like standard atomic types for simple operations to provide synchronization without the overhead of mutexes. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.